Good afternoon, everyone. So you can see a picture here, right? So water droplets on the lotus leaf. If you take water drop in your hand, will it be like this? No, sure, right? So what is happening here? See, when the water drop is taken on a lotus leaf, it forms a sphere, right? Otherwise also water drops are spherical in shape. Can you tell me, can any of you tell me what is the reason that the drops are spherical in shape? Yes, Harinanda, tell me. Stand up.
The surface area of the water droplet.
Yes, sit down, good. So it is due to surface tension, right? And here, this water droplets will it wet the surface? No, right? It will not wet the surface, but it will wet our hand. The reason is that there are two types of forces. Do you remember the two types of forces? Yes, Meera, can you tell me?
Cohesion and adhesion.
Cohesion and adhesion. Yes. So adhesion is a force between yes, Sudhir. Unlike molecules, yes, it is the force between different types of molecules. So here the force of cohesion is more. That is why it is forming a drop. It is not wetting the surface because the force of attraction between the lotus leaf and the water is less compared to the force of attraction between the water molecules. And this is due to the surface tension, right? And if it is a drop, then if it is forming a drop, then there will be an excess pressure inside the drop. Last class we derived the equation for the excess pressure, right? Can Shraddha, can you tell me the?
R is the radius of
Yes, Sana. The equation is Pi minus Po is equal to 2S by R. Okay. So now we are going to study a different phenomenon, based on the surface tension itself. Okay. To understand that, we will move to this video. Right.
How do plants transfer water from their roots to leaves?
See, when you see this heading, what do you feel? You feel that this is a biology topic, right? But physics is there in everywhere. In biology, chemistry, wherever you go, you can see the physics in it. Now it comes like this. Yeah.
One of the biggest challenges that space programs worldwide face is the high cost of fuel. It takes at least 6 to 7 kilograms of fuel to launch 1 kilogram of payload into the orbit around the Earth.
See, it takes 6 to 7 kilogram of fuel. Okay, because what is the reason? If it has to move up, then it has to move against what? Gravity, right? So if it is moving against gravity, a large amount of work should be done.
This is because of the enormous pull of the Earth's gravity. Any object thrown upwards from the Earth's surface slows down at a rate of 9.8 meters per second square.
Something that you know, right? Yeah.
Hence, it isn't easy to move anything against gravity. Yet, trees are...
But think about the trees. These trees are very, very tall, right? And they grow. For their growth, what is required? Water is required. And from where do they get the water? From the soil. Okay? That means the water has to move from here to the tip. So this water is flowing like this. It is moving. See, if we have to take water from the well to our tank, what do? We have to keep a motor, right? And 1 HP, 2 HP, we have to do, you use the electricity, we have to do a lot of things. But here, water rises easily, okay? And you know the reason, last year you have studied, what are the two tissues present in it? Xylem and phloem, yes. So because of that it is happening. So we will see what is the reason that water is rising through the, against the gravity. Okay, and you can see many other examples also. See, look at this. This is something that we do every day, right? Now in this, see this wick, the oil, only this end is touching the oil rises through this clothes to this tip. or if it is this type of lamp, the oil is present here, the wick is inside, so this bottom is touching the oil, and the oil rises through and it reaches to the tip. So in all these examples, what we can see is that the liquid is rising against the gravity. So this phenomenon of rising against gravity is something that we are going to study. Before that, we will see one more experimental setup. See, in this experiment, in the setup, okay, see, we have seen similar picture when we studied the Pascal's law. You remember hydrostatic paradox? In that, the level of water was same, but here what do you see? What we can see is that in this, the water level is here, and when you move to the next one, see the third one, if we draw a straight line like this, we can see that when from this tube, when it moves to the next tube, we can see that there is a small, see, there is a rise of water, right? And as we move to the next one, some more is there, then some more is there, and here very large rise of water is there. See, what is the basic difference between these two tubes, all these tubes? When you compare this tube and the last one, what is the basic difference? What is it? Thickness or the radius, right? So the radius of this tube is very, very, very small. Okay, so a tube of very, very small radius is called capillary tube. It is called capillary tube. A tube with very, very small radius is called a capillary tube. Okay, see the word meaning of capilla, the word meaning is hair-like, the hair-like. Okay, so here we can see that when the radius of the tube is decreasing, when the radius of the tube is decreasing, then the level of water, I am showing it as the height is increasing. Okay, that means when liquid or when a capillary tube is immersed in any liquid, we can see that there is a rise in it. See, have you seen capillary tube in the lab? You have seen, right? Yeah. Now this is an ordinary tube. When this tube is immersed in it, you cannot see any rise of water. It's like almost the same. The level is the same itself. But instead of that, if we are immersing a capillary tube, this is a capillary tube. See, you feel that this tube is very thick, but inside that hole is very small. Okay, all of you have done the experiment, I know. But now if I am immersing it here, you cannot see it immediately. There is air, okay? Yeah. Now can you see the level? Okay, you can see it, right? Okay, so you can see the level. It is inside, it is rising. Okay, can you see it? Yeah. Right? So you can. So if a capillary tube is immersed in a liquid, through that tube water or the liquid rises. So this phenomenon is called the capillarity. It is called the capillarity. The phenomenon is called the capillarity. I will give you the definition later. Okay. So this phenomenon is called the capillarity. Now, what is the reason for this, or is it always a capillary rise? To understand that, look at this. See, when a capillary tube is immersed in it, okay, see, it's water, it is taken, it is written here H2O, water is taken, and water when it is taken, will it wet the surface or not? Water, what is its property? Will it wet the surface? Yes, it will wet the surface. So if it is wetting the surface, then we have already studied that, then the meniscus formed will be concave or convex? Concave. So it is forming a concave meniscus here. And if it is a concave meniscus or if it is a drop like this, then the pressure inside is Pi and the pressure outside is Po. Then we have studied that there is an excess pressure Pi minus Po is equal to 2S by R, which means at the concave surface there is an excess pressure. So why the liquid is rising through this capillary tube is to balance the pressure, because the pressure at this level should be the same. Pascal's law states that pressure will be same. So if the pressure has to same, then the liquid has to rise through this. But there are other liquids which will not wet the surface. Which is the liquid which is not wetting the surface? Mercury. Yes. So if we take mercury, okay, if we are taking mercury, right, see, it is forming a convex meniscus, okay, which means if it is a convex meniscus, then the pressure is more here. Pressure is always excess at the concave side, okay. So here the drop is formed in this way, so the pressure will be more here. Again, it has to balance the pressure. The pressure should be same at this level. To balance that pressure, instead of rising through the tube, what is happening here? There is a fall of liquid is happening. Okay, so it need not be always a rise through the capillary tube. It can be a rise or a fall. So this phenomenon of rise or fall of a liquid in a capillary tube is, compared to the surrounding, is called the capillarity. Okay, so you can note down the definition. Capillarity is the phenomenon of rise or fall of a liquid in a capillary tube in comparison to the surrounding. Now we have to derive an equation for the height or the capillary fall. To derive the equation, we move to the next picture. Okay, did you write, all of you? Yes. So to derive the equation, now look at this picture. This is happening actually. When a capillary tube is immersed in a liquid, there is a rise. The h is the capillary height. Okay. Now we know that, see, the pressure at this point, okay, yes, pressure at this point is written as PO. Alright, why is it written as PO? Because we are considering this as a drop. Okay, it's a drop, you know, drop. Then the pressure inside Pi and the pressure outside is PO. So that is why we are here, we are writing it as PO. But since it is a air drop, it's not a water drop, it's an air drop, it is forming a concave, so it's an air drop. So here the pressure inside is the atmospheric pressure. Okay, so it is written as PA. Hope it is clear. You can see, right? So it is PA. Right. So this is PO and this is PA. Okay. So tell me, which will be high, PA or PO? PA or PO, which will be high? See, it is a concave meniscus or it is forming a drop. So which will be high, PA or P? Which is high, the pressure inside or pressure outside? Inside is more. That means PA is more than PO. Okay, that means if we take this as a drop, then this is Pi. Instead of Pi, PA, and the point here is PO. So we can write the equation PA minus PO is equal to 2S by R. Pi minus PO is equal to 2S by R. Alright? Okay, so this R, small letter R is the radius. Okay, small letter r is the radius, small r is the radius. Now, see the pressure at this point A and the pressure at this point B will be same. Okay, pressure at the point A and the pressure at the point B will be same because they lie on the same height. See, from here we can write PO is equal to PA minus 2S by R. Okay, PO is equal to 2S by R. Now, okay, right. See, pressure at A is equal to pressure at B. What is the pressure at A? Isn't it open to atmosphere? So what is the pressure acting at A? Atmospheric pressure, P small letter a. It is equal to, what is the pressure acting at the point B? See, at this point B, see, since this surface is open to atmosphere, here PA is acting plus the pressure due to that height also is acting. So the equation becomes the pressure at this point, which is PO, plus pressure due to the column of liquid, that means rho g h. Pressure due to the column of liquid, that means rho g h. That is equal to, we can substitute for PO. PO is equal to PA minus 2S by R plus rho g h. On the LHS we have PA. The PA will get cancelled and we get the equation rho g h is equal to 2S by R. Okay, rho g h is equal to 2S by R, or we can write the equation for the capillary height as h is equal to 2S by R rho g. Okay, but is there any problem with this equation? This equation is okay, simple, but see, what is this R? Radius of what? Radius of that concave meniscus, right? Is it easy for us to measure the radius of that concave surface? No, that is not easy. So we have to write the equation in terms of the radius of the capillary tube, because capillary tube is something that we are setting. Okay, so instead of small letter r, which is the radius of the concave meniscus, we have to include the radius of the capillary tube. To do that, okay, that is, we need this picture. Yeah, see, what is this angle? This angle, is it angle of contact? It is angle of contact theta. Now this angle also will be same angle of contact itself. What is the reason? See, this surface and this surface, the angle between these two is theta. Now this line is perpendicular to this surface, and you know this the tangent and this radius will be always perpendicular. So the angle between these two and the angle between their perpendiculars will be the same. Okay, I think I'll repeat it. Okay, see, yes, so this angle is the angle of contact theta. Okay, now this line and this line, these two are perpendicular. Yes, and what is this actually? This is the tangent, isn't it? And tangent and radius will be always perpendicular. Okay, so the angle between these two and the angle between their perpendiculars will be same. Okay, angle of contact theta, and here the angle between these two also will be the same. All right. Okay, so Now in this picture, this is theta. So if we take cos theta from it, cos theta equal to, see, this side is A and this is R. What is cos theta? A by R. And what do we want? We want the R, right? So R is equal to A by cos theta. R is equal to A by cos theta. Now we got the equation. See, rho G H is equal to 2S by R. This is the equation that we got. Here we can substitute for R, that is 2S by A by cos theta. 2S by A by cos theta, that becomes 2S cos theta by A. And on the LHS we have rho GH. Rho GH is equal to 2S cos theta by A, or the equation for the capillary ascent, that means H is equal to 2S cos theta by AGH. So this is the equation for the capillary height. Now if it is, sorry, it's not H. It's AG rho. It's AG rho. Okay, this is the equation for the capillary ascent. Okay, now if it is capillary, if depression is happening, then when we do the calculation we will get a negative value. That is the difference. If it is positive, we can understand that there is a capillary rise, and if it is depression, then that value will be negative. Okay, so this is the equation for the capillary height. Okay, done. Now can you tell me why there is a very small, hole is made on the nib? What will be the reason? So that ink comes through it. It acts as a capillary tube. Okay, it acts as a capillary tube. Now did you get the answer why? How the water is rising through it? What is the reason for that?
Brahma Panam Brahma Hari Brahma Ko Brahma Rahubam Brahma Vadena Gantavyam Brahma Dharma Samadhina Hari.
So what is the reason for the water to rise through this? Because the tissues which are present in it are very thin. It acts like a capillary tube. So through this capillary tube, the water rises to the tip. Similarly, in that wick, wicks which we keep in that oil, the lamp and all. See, do we use any kind of cloth to do that? No, we have to use the cloth which has got a very small holes in it. Okay, so through that hole, the water rises through it. And other examples like tissue paper. Why do we use tissue paper? Do we use any kind of the newspaper will you use to we will not use that, right? What is the reason for that? The tissue paper contains, it has got a particular texture, isn't it? So the tissue paper contains small holes. That means capillary holes are there. So it is through the capillary holes that the water is rising. Okay, then can you tell me any other examples? Anything else? As a bathing towel, what do you use? You cannot use any kind of you use the cloth with some kind of holes, isn't it? So different things are used there. So in all these cases we are using the property that means capillary, okay, capillarity, okay. And one more interesting thing is that, see, in our country, what do we do before the summer starts? Have you noticed that the farmers plow their field? Have you noticed that? Okay, see, after the rain, before the summer, they plow the field. So the reason is that, see, it is soil, right? Soil contains a number of small holes in it. Capillary holes are there. So it is through this holes, there is a possibility that the water rises up and the sand, the soil will get dried up. So what should be done? Before the summer starts itself, they plow the field. So when it is plowed, all these capillary holes are closed. Okay, because new soil will come on the top of it. That is the plowing means just changing the texture, everything. So what happens is all these small holes will get closed. So there will not be any capillary, due to capillarity there will not be any water loss. So the soil remains wet itself. Okay, so that was something which was, without even knowing that it is due to the capillarity, our culture, it is there in our culture. Okay, so that is another example. Then so can you tell me answer to some questions, simple questions based on it? Yeah. Yes. Choose the wrong statement from the following. Small droplets of liquid are spherical due to surface tension. Is it correct or not? It's correct. Then oil rises through the wick due to capillarity. That also correct. This is correct. This also correct. Then the next one, in drinking the cold drinks through the straw, we use the phenomenon of capillarity. That's not there. What is the reason? The holes are very big. It's not a capillary tube, first of all. Then the second thing, we are using, we are sucking it. So that is so this is the wrong answer. Okay? Yes. Next question. Two capillary tubes of different diameters are dipped in water. The rise of water is same in both tubes. Will it be same? No. Greater in the tube of larger diameter? No. Greater in the tube of smaller diameter? Yes. Independent of the diameter of the tube. So the answer is 3. Greater. Okay? Yes. Okay. A liquid rises in a capillary tube if the angle of contact is acute, obtuse, pi by 2, pi. What is the reason? Acute. So if it is obtuse, what will it be? There will be a capillary depression. Okay. So if it is acute, there is capillary height, and if it is obtuse, there will be a capillary depression. Okay. Now water rises in the plant fibers due to osmosis, fluid pressure. Answer is capillarity. Which one of the following statement is correct for capillary action? If theta is less than 90, the liquid level rises, and greater than 90, the liquid level falls. Is it correct or not? Yes. Then if theta greater than 90, no need of, is correct, right? The first one is correct. Okay. So these are the questions. Now, see, by when detergents are added, then the surface tension will decrease. When detergents are added, the surface tension will decrease. So what will happen when we take a normal water and detergent added water, when in both solution, when capillary tube is immersed, which will show more height, the ordinary water or detergent water? Ordinary water, because surface tension is more in that case. So the quality of the detergents can be checked by using this. Okay, we used to do an activity. Different detergents were taken and we measure the capillary height and we can understand which one is the best detergents, because when the surface tension decreases, its cleansing capacity also decreases. Okay, so which is the best one can be understood in that way. Okay, so that is about the capillarity. Okay, got all of you? Right? Okay, thank you children.